efficient diagnostic test for cooties. So we're going to examine a manufacturer that did put together a test for cooties. So let's take a look at this test. Well, I'm going to build a table. Sometimes we call this crosstabs, but it's a table basically, a 2x2 table. Okay, and this table has in the columns whether or not a person has a disease, right? So the variable in the columns is disease. They have cooties or they don't have cooties. In the rows, in the horizontal rows, it has whether our diagnostic test tested positive or our diagnostic test tested negative. Well, we know very well that diagnostic tests have a lot of issues. Sometimes they work very well, sometimes they don't work well at all. Okay, so we're going to take a situation where we're looking at any disease that we want to look for, examine, and we want to evaluate how good a diagnostic test is. This is what we're looking at in general. Okay, positive test, or T plus, is in the rows. In other words, anybody in this top row tested positive. Anybody in the bottom row tested negative. Anybody in the first column has the disease. Anybody in the second column has the disease. So let's take a look at this. This person over here has the disease and tested positive. We call that true positive. That's what's the TP stands for. This person tested negative. He has the disease, but he tested negative. So we call that a false negative. Let's go over to people that don't have the disease. If they don't have the disease, you want them to test negative. That's a true negative. Anybody that's in that box is a true negative. Okay, anybody that's in this box is a false positive. They tested positive, but they don't have the disease. They're in the column of people that don't have the disease. And then at the end here, we're just adding things up here. Okay, just one other thing here. Total number of people with the disease out of the total number of people in the population or in the sample. What is that called? The number of people over the total number of people? What's the name for that? Number of people in a population that have the, right, bingo, prevalence, exactly. Good. Okay, so now that we know that, I'm going to go back here. I am going to call the efficiency of how good a test works. I'm going to call it its sensitivity. In other words, I'm going to say that the sensitivity of this test that we've developed for cooties is that 80% of the time it will correctly identify a person with the disease. Well, on the other hand, what about a person that doesn't have the disease? Well, I'm going to say that 90% of the time you'll get a negative if a person doesn't have the disease. And I'm going to call that the specificity. Okay, I'm going to work with a population that, say, I'm assuming has a prevalence of 10%. And I'm going to say that this is how we think this test, that's how good we think this test is. Okay, so I'm going to use this information, and starting with 1,000 people, I'm going to fill in everything else that's in this box. I have all the information I need for it right here. Okay, so for starters, let's see, the total number of people that have the disease are here out of the population, which is 1,000, or the sample, which is 1,000. So 80%, let's see, the prevalence is 10%. So out of 1,000 people, how many people have the disease? Right? It's going to be equal to 100 people. 10% of the people have the disease. That's all that prevalence is. So if 100 people have the disease, that means 900 people don't have the disease. Okay, so now let's take a look at what we would expect this test result to look like. If 100 people have the disease and the sensitivity of the test is 80%, we would expect it to get this right 80 times. Out of those 100 people, it'll identify 80 people that have the disease. That means it's going to miss 20 people also, because sensitivity is not 100%. Similarly, if we have 900 people that don't have the disease, then we know the specificity is 90%. So we know that 90% of the time it'll be right at identifying people that don't have the disease. In other words, saying they're negative. So the number of people that are true negatives is going to be 900 times 0.9. Or we'll get it right 810 times. That means we're going to get it wrong 90 times, because there's 900 people that don't have the disease. 10% of the time we're going to be wrong, that 90. Okay, so total number of people that tested positive, it's going to be 170 people. Total number of people that tested negative is going to be 830 people. And there we have it. We have our whole table laid out. Okay, in fact, here 170 and 830 indeed add up to 1,000. Well, okay, so we know that, but one of the things that as a physician, as a health worker, that you might be interested in is, well, or even as a person, you go out and you go to the doctor. Doctor, I have this strange scalp itch and I think I may have cooties. And could you do a test for me? And the doctor comes back and says, I'm afraid you've tested positive for cooties. You're going to want to know, well, if you test positive, and he's going to send you, of course, trust me, I've been through this in our current health system. The next thing he's going to do is send you to a cootie specialist, because there's a specialist for everything now. Okay, so now he's going to send you on to a specialist. It's going to cost a lot of money and so on and so forth. You may be interested in knowing, well, that positive test, how good is that test? What's the likelihood that I really have cooties if I tested positive? That is called the positive predictive value for that test. Okay, what's the positive predictive value? The positive predictive value is the number of true positives over the number of true positives and false positives. What does that mean in English? That means that 170 people tested positive, true positives and false positives added together. This is all the people that tested positive. 170 people tested positive. Only 80 of them actually had cooties. So the positive predictive value of this test is equal to 80 out of 170, which is 0.477, 47%. There's a better chance that you don't have cooties than that you do have cooties, is basically what that says. Slightly better chance. Well, let's take a look at another value that's very useful. Negative predictive value. Same idea except with negatives. If all the people that tested negative, what percentage of them actually are negative? How good is that negative test at predicting that you're negative? Okay, let's take a look at this. Out of the 830 people tested negative, and 20 of those people are false negatives. They're wrong. 810 people are true negatives. It was correct. So the positive predictive value of this test is 810 divided by the false negatives plus the true negatives, the total number of negatives, in other words, 830. Okay, which is 97%. You can be 97% certain that you don't have cooties if you tested positive for this test. Here we have a measure that you can, as a physician, work with, as a healthcare worker, work with, as a patient, understand that if I get test positive, it's still 50-50, right? If I test negative, it's still, I'm pretty sure that I don't have it. There's a pretty good chance I don't have it. Not a bad test, but that being less than 50% positive predictive value, that's a little bit of annoyance, isn't it? Because you may get very worried about it. You may be socially ostracized if you're like 11 years old, and so on and so forth. So, on the other hand, it's also going to cost money. You have to go to a specialist. There may be more extensive testing, more invasive testing, painful testing, dangerous testing that may take place because a lot of people didn't have the disease. Let's examine something interesting here. Let's see the influence of prevalence on how this works out. We're going to take exactly the same test, right? Except this time the prevalence is 1% instead of 10%. We have a disease that's not very prevalent. We test 1,000 people for this disease. Out of those 1,000, we would expect that, well, now it's only 1%, so only 10 of those people are going to have cooties. Not 100, only 10, 1% of that 1,000. Well, sensitivity is 80%, so that means we'll identify 8 of those people correctly, and 2 of those people will incorrectly tell them that they were negative. Well, okay, so that leaves 990 people that don't have the disease. Okay, how many of those 990 do we correctly identify? Well, 90% of them, right? Pretty good specificity, right? It gets it right 90% of the time as far as the negatives is concerned, times 0.9. Okay, so we correctly identify 891 people. How many people do we incorrectly identify as that are negative, and we don't, and specific, they're the 10% that we get wrong? Well, that's 99 people. That 10% out of the 99. Add these together, adds up to 990. So we know that's, I think, right? Yes. So we know that's right. So how many people in this population tested positive? Well, we got 107 people that tested positive, and we get 893 that tested negative. What's our positive predictive value? If you're one of those 107 people who tested positive for cooties, what's the likelihood you really have cooties? Okay, let's see. Equals. Let's see. We've got, there's 8 people that really have cooties out of 107 that actually tested positive. Gee, only 7% of these people have cooties. Okay, well, how about negative predictive value? Let's take a look at that. Out of, let's see, how many people tested negative? That many out of 893. Well, 99 point, almost 100%, right? That's pretty good. Pretty good at screening out people that don't have the disease. But I see a problem here. Okay, and that problem is that our positive predictive value is only 7%. So what happened here? It's the same test, the same disease. Here it was correct about 50% of the time. Here it's only correct about 7% of the time. 93% of the people that are going on to specialists for further testing are going to find out that they don't have the disease, and they're going to spend more money, and they're going to have more invasive testing, and so on and so forth. Okay, what happened here? The prevalence influenced the positive predictive value of this test. Any of you think of a situation? Can any of you think of a situation where you have a disease that has a low frequency in the population? You're screening a lot of people. It's got a low positive predictive value, and you wind up doing a lot of other invasive testing as a result of a positive test. Anybody think of something like that? Breast cancer, bingo, great. PSA, oh, thank you very much. PSA screening. I got to tell you, half the people I know at my age have had had a war with a urologist over PSA testing, right? And breast cancer testing, of course, also, right? Every time a lump comes up or some other test or mammogram and find something and so on and so forth, there's more testing. Most of the time, positive test on a mammogram turns out to be something else. Now, there's certain situations where that you'll accept that anyway, because the consequences of not following up are so dire, right? But when it comes to healthcare professionals who have to make judgments as to where to spend money, available money that that might go somewhere else that would be a more effective, save more lives, be a more effective treatment, be less invasive, and so on and so forth. You got to make some hard judgments. Understanding how these tests work is really important to understanding how we're going to deal with